Yes, we are back online. 10 minutes break over already. So let's say we go down. 3D plots, very good. Now, take the same data as above, which is basically a product of cosines in different directions, looped with a Gaussian. Actually, just multiplied with Gaussian, and what you see here is the projection on a grid in data in 3 dimensions. The alignment on the intensity again is not really given at 0. We can try to fix this later. But that's what we are after. And what I want to highlight here already is that some of the data is hidden. For example, here is a peak, right? Somewhere, what is x? Maybe 2.55 and y maybe, I don't know, it's very hard to read this one, right? So this could be y equal 0, but no, this. So, you see, it's not actually easy to find now the real points, because the 3D plot makes that harder, plus the peak I try to indicate is hiding information on the peaks behind it. So it's not really recommended, but just because it's not recommended in this case, I can say it's never recommended. There are cases which can be very impressive to use, but you need to choose your tools carefully, right? Don't only do something because you can, you must have purpose behind it. So, anyhow, how do we get the 3D plot running? For the 3D plot, we actually need to go to the very, very top of the document and see that we added a special module. Let's see. Can I find it? No, it's not. Okay. Can't find it now. Laptop is also hanging a little bit because streaming, capturing the screen, and me scroll through a Jupyter notebook is a little bit much. Stop pushing the button, still going down. Who knows? I try to go up, but it's still going down. Yes, okay. Oh. So now my laptop is. So I'm not touching anymore, right? But it's like I'm touching. Ah. Can you see that? Oh. Oh. Done. Yeah, the laptop is done. Very good. Okay. Okay, so what we do is in the subplots method, we asked for additional an optional argument where we specify the projection to be 3D. Do you see this data structure here? What is this? What I highlighted? It's a dictionary, right? So far, so good. Dictionary, right? Projection. P as projection, value is 3D. Let's try to execute first if things actually work properly as they should. Okay. A little bit funny, no? Need to fix something. So what I need to do here is I need to restart my kernel. Restart. I need to re-execute parts where I load my modules. difficult to find, so I just retype it. So first is numpy, then it's matplotlib. And pyplot. Try again. So what most likely happened is that I changed a few details of the plotting backend here in the animated part that I run quick. Max is not defined. Fix that. And then things are not that compatible. That is not defined. And fix that too. That's my Z over here. So now we should have fixed the data or adapted in a way, make it bring it to the right state in memory, so we can proceed with 3D plot. Yes, and this is how it was before, right? So if we follow the script through at this point, it still works, at least for me. I hope it works for you as well. And now we can again look at it step by step. Line 4, we create a figure and axis object with the specific figure size. We can make it slightly smaller. And then in line 5, I use the plot surface method. So that is again very similar to F. I have a syntax of X and Y grid information, the Z value. I can choose a color map and anti-aliasing to make the plot appear with higher resolution. That's a thing from the 90s actually. Nowadays the screens are so high resolution you don't need this anymore. Here we go when we have not chosen these values. What is this? I'll remove this one as well. So what we, however, run into is some rendering mistakes. So we see part of the grid information instead of the implicit height. So we put the arguments back. And we have our beautiful plot back. Now we should have an on function. Let's see if we can apply an on as well. And we can center it around 0 in the intensity scale, right? Okay, so this is the recommended way of plotting it because it shows a proper alignment at a reference 0 that then clearly separates positive from negative regions. Please also note at labels X, Y. Now Z is basically the Z information is given twice, once through the 3D projection and the other time through the intensity. So when you give the scale, I'm like, okay, information is there. If you don't give the scale, you must give a label here on the Z-axis. So far, so good. In principle, I feel like I've said that before. Did I? Have I shown you like this? We can try the Z label. Right, we can do this as well. X, Y, Z. Put Z here now. This is a little bit contradictory, because the label can be either zero intensity, but giving the same information with different labels is a little bit confusing, right? So you can add the z-axis label, but keep your data presentation consistent. Okay, so far so good? Yes, no, maybe? Easy, difficult? Neither nor, but quite a lot, right? So this is something to practice a bit, right? Put into your toolbox, and then the optional part, animations. So animations you cannot put in a scientific report, right? But you could put on your personal website, you could put in a presentation. It lifts normally people's attention, right? Because there's something to look at. So let's see. So animations, you know what it is, right? It's pictures that change rapidly. So when you look, do you look cartoons? Are you doing such things as a child? Cartoons? Bugs Bunny? What else is there? Cartoons? No? Pokemon? Pokemon? You watched Pokemon as a kid? Yeah, very good. Pokemon is a cartoon. How do they do Pokemon? Right? In the olden days, there were animators drawing picture by picture, right? With small changes, and if you run them very quickly, you see things moving. We do the same now with Matplotlib. Let's execute the plot first. Right? So we already see it's like a movie, right? It's a little bit jerky, right? Right? Not very smooth, but yes, I see something. Oh, it's a sine function. So it's going down. Oh, so nice. Oh, okay. So interrupt, right? Because it's taking CPU resources. By the way, the live stream is working or not? Obviously not, because it's working, right? Bitrate is low. Is it? Anybody can confirm anything? Okay. Looks like something is working. Bitrate is slow. Okay, so animation is fine. The code is a little bit more complicated, because what we need to do is we need to tell Python what we want to have and how it is supposed to change over time. What we want to have is basically a sine function that grows over time plus a marker of a square that is at the very end of the growing sine function. Okay, so how do we do this? We import some modules, right? So animation from matplotlib animation, import animation. Well, that's a new thing. We also changed the plotting backend, right? Because the ordinary one, at least in my setup, is not compatible with animations. So I need to basically tell matplotlib, hey, use the notebook plotting backend. Okay, so in line 7, I again prepare X data, and in line Y, I prepare Y data. So at this point, I have a normal sine function, X and Y. So we just take X and Y and plot, PLT plot, we get the sine function. What we need to do next is some preparation for the plot. And we are going to prepare an empty X object. So we can copy this part for some else and see what we actually have at that point. Empty, right? So far, so good. But this is basically our drawing board. Now, what we need to do next is to find the data we let grow over time and insert in this plot. this is what we do here. But first is the sine graph, which is again an empty plot object. Look what I do here. Sine graph is axis, plot, empty data. But I catch the return value, the handle to that axis object in sine graph. I do the same thing for something that I call dot, which is a square in green. Basically, it could be a scatter plot, it's just one point I'm putting there. Right? But I then now add data. For example, I have pen data, or I increase the slicing of my data. I can update the amount, the choice of data I put in the plots. So then I define here a plot sine function, which takes an argument I, and I is an eta bit, saying, hey, take the data from x and y from 0 to I. Now, at the beginning of the animation, I could be 1, right? So then I just have 2 points. But then I let I increase with every frame. So I goes from 1 to 2 to 3, 4, 5, 10. So I will say, right, at frame 10, take the first 10 points of my sine graph. At frame 20, take the first 20 data points of my sine graph. So here, how do I communicate now the data into my plot? I already have the axis object and the handle to the axis object as sine graph and as dot. What I need to do is update the information in this axis object. I'm doing this with set data. So I have this object, and then I just say the data has changed, updated. Right? That is set data. And here, again, see the index slicing notation from 0 basically to I. In x and y, and for the dot, we just choose the last point. Right? So here, this is just one point in x and y, point I. And over here, line 19, this is the data from 0 to I. Well, then, the animation will be called an animation, animate a function, the handle to the figure object, the function that is supposed to be plotted, the number of frames. I know I have n data in my x-axis, right? So I choose the length of my x-axis, and the interval I say 100. This is 100 millisecond is supposed to be separating the frames. Now in your movies, you have a frame rate of like 24 or 25 frames per second, right? So we can actually decrease it a little bit to make it smoother. Right? And execute again. Does it work? So it's a little bit jerky again because my CPU has to render the animation, has to record and live stream. That's a little bit much maybe. But in the end, we see one beautiful animation, and in principle, you should be able to save the animation or the plot as well. So far, so good. A little bit easy, sorry, a little bit difficult, but right, think about it, it's really just drawing many pictures and separate them over time. This, by the way, is not the only way you can have an animation in Python and with Matplotlib, but this is the one I found to work on my laptop. In previous years, I've given this code to students. They tried it on their machines, and it didn't work. There are other codes you can find online. I tried on my machine, didn't work. Right, so it's a little bit technical. Also note, for me, it makes a big difference if I have this first line here, setting the right plotting backend. It used not to work unless I have Matplotlib basically talking to the notebook itself and not the plotting routine. So it's a lot of things can go wrong. try it out, see if you can make it work. If not, I'm here to help as much as I can, but there are also limits to this because I don't have, it's your machine, or not my machine. So you know your machine best. Okay, and with this, we are basically done with the animations and the plotting. Are there comments or questions? Right, so now you're all experts in plotting. You know as much as I do, and I'm looking forward for some very, very nice, elaborate plots. If there are no comments or questions, then we can go to part 3. Or chapter 3. Chapter 3 is about symbolic computing with SymPy. So like NumPy, that is for numerical computations. We can perform symbolic computations with SymPy. Now my question. Have you ever done symbolic computations? Yes, you do. You do this in high school, you do that at university a lot. Yeah, symbolic computation is when you define symbols like X, Y, Z, A, B, C, and then you solve equations. You find values for uh, some symbols, some variables on pen and paper. For example, find the solution of x squared minus 4x plus 2. You know what to do, right? With pen and paper. Now the question is, can we find a way to have the symbolic or analytic computation capabilities with Python? Could be quite handy, right? If you have an integral to solve, like sine x squared plus whatever, and you can ask Python for it, that would be great to see if what you did was actually correct or not, or if you need to practice. Right? Same for differentiations. Same for step operations. Okay, so the obvious answer to this introduction is if you use SymPy, you can do symbolic computing with Python. And then whatever you do at university with a paper in some form of equations, in principle, you can always try to verify it with a SymPy. Okay, so the aim of this chapter today is, which of course we're not finished, but we try as much as we can, introduce SymPy, work with algebraic expressions, solve equations, and perform a Taylor expansion with SymPy. So what we're going to need to do is to look into a computer algebra system. Right, so we already have learned algebra. Now we need to find a way to use the computer doing some algebra. So what is algebra? What is this one here? What a mix-up of language here. Algebra. Algebra is a type of math in which letters and symbols are used to represent quantities. We want to basically provide a means to potentially automate these calculations. Right? If somebody asks you to Taylor expand a function, plot the result, compare, then you can write a Python function, do that in the future for you, put in the function, put in the numbers, put up the range, push a button, get the result done. Our aim is normally to get some form of analytic insights using well-defined logic, right? Because maths only, or in science itself, works only if we have logic to build understanding, and especially look for all parts separately, right? Okay. Try to, so this may be hard to get, but analytic and numerical computations are tools we use which have their own purpose. So analytic calculations, we normally evaluate and build models. Numerical computations we do when we have a lot of data, either validate our models or test a numerical hypothesis or a rule that require a lot of data, for example. Okay, so let's use SymPy. To use SymPy, we have to import the new capability into our Python backend. We do this by import SymPy as whatever you want to call it. Like other people, normally calls it SP. So far, so good. Basically like NumPy, but instead of n, you put x. Then let's skip one step and import some constants. Right? In NumPy, we have constants defined, and SymPy also has. So from SymPy, I import pi, and the last one is infinity. How do I write infinity? Two O's, right? O, not 0, 0, or O, small ones. And then look at the value of pi. Oh, it's okay. What else? We can define some functions, but you must clearly distinguish between math symbols and Python objects. Right? So the Python objects store information of a symbol. The symbol itself, what it represents, might be something different. For example, we have mathematical symbols, x, y, f, g, and sign function. Examples of Python objects is my array, my list, x, y, z, blah, blah, blah. So we can use any of these objects to store the representation of data associated with the mathematical symbols. So far, so good? I normally call it on my list or my sign or my array, right? And I put the values of x into the sign function and store the result of the sign function in that access object, array object. So, right. So the next thing is we need to introduce our mathematical operations, which itself are actually characters. So we have to define an equation, y equal mx plus n, mathematical operations of symbols equal, multiply, and add that are part, right, that connecting terms of that connect terms to an equation. Now, equations only state the relations between symbols, so we know when we see an equation, if the solution is could be an integer, could be a complex number, could be a real number, we need to solve the problem to know what it is. So let's see. We have imported SymPy. We know how to load some constants. Now we want to build a simple equation. And the first ingredient to your equation is your variable. For example, x. So the variable or the symbol is one thing. How you store it in Python is another thing. Our variable is often x. So what we want to define next is just the symbol x. To do this, I call sp symbols, string of symbols, and some additional restrictions which I will explain or put into use later. So real and positive could limit values of the variable to either real values or positive values. Right? So this is the syntax that we generally use. Now the example on how to make use of this method is simple symbols, string of symbols, that is x, and we store this in the Python object symbol x. So far, so good? So now when I get access to, when I want to have access to the variable x, what do I type? I type x? No. X is not defined because x is not a Python object. X is the value stored in symbol x. Right? So clearly distinguish, hey, this is my information, and this is my Python access to it. So I want to have access to symbols, to x. I need to use the Python variable or Python object that stores that information. So when I want to say, hey, y equal x squared, I can write y equal symbol times symbol x. Here's the x. So far, so good. Y contains x squared. At least it should contain. Okay? So clearly distinguish the variable and the symbol and the Python object containing that symbol. We did the same thing again with the sign function and its values. We always store that information into the variable containing the array information. Here it's the very same thing, just that we don't know which values x specifically has. Could be any value, we haven't specified it. But the Python object tells you, yes, there is some symbol with possible values. We don't know yet. They are there. Now, I know this is a little bit confusing to work with. So the way to handle this, or how I use it in practice, is I make my life easy. Obviously, right? So I call the symbol and the variable to have the same syntax. But when I code, I clearly know when to use the symbol and when the variable. Yeah, this is also important. So if you struggle a little bit to distinguish the meaning, give it different names. If you can work your way around this issue, you can do whatever you like on it, basically. So I normally do like this. And then it's much easier to read here x times x equal y instead of symbol x. So far, so good. So do what you like. You have the freedom in Python, but be on top of your data structures you use. So what else can we do? We can define several symbols at once. For example, here I define 4 symbols because the symbols method takes a string as input and converts them to outputs. So far, so good. And I think we can even put in some Greek letters. You see that? So I have here X, Y, M, and N. that catch the return values of symbols. I plug in a string xy alpha in. So the third entry is supposed to be a Greek letter. Right? In Python or Simpa is clever enough to say, hey, the third entry goes into M, and when I call what is M, it will tell me alpha. So far, so good? Now this is a little bit dangerous because if I'm very careful, I could, for example, mix up in this symbols definition the symbol and the variable, and then Python will put x symbol into the variable y and the y symbol into the variable x. If I work with this and I'm not careful on what I do, this could be a very, very difficult error to find. And because Python is not complaining, then you again need to check all your data very, very carefully. So be very mindful what you do here. It's very easy to make mistakes at this stage. We have access to Greek letters. The Greek letters I would normally write out as a Python variable or object and as a symbol in symbols as well. I check alpha, alpha. So far so good, right? So now when we have the symbols, we actually can combine them to equations. So here I have a very simple equation. I know x times n plus n equals y. I call what's in y, and I know, yes, mx plus n. That's a linear function. You know m and x are parameters, and x would be your variable. Python, however, everything is a symbol, and you need to be a little bit careful how you, which symbol you treat as variable and which as a parameter. Do you know the difference between parameters and variables? When is something a variable and when is something a parameter? Did I do this exercise with you before? I do this every year, so I'm getting slightly confused these days. For example, when I go to the doctor, they put me always on a scale, right? What's the weight they show? Let's say 100 kg, right? Okay. So how do you calculate this? What do you need to do? The scale is measuring a force, actually, right, or some pressure. So how do you do this? Then force is what? Gravitational accelerations, right? G, 9.81. Unit is what? Newton per meter, okay? Kilogram, something like this, right? Actually, it's meter over square second. Sorry. And then my mass, right? And that would give me a force, and that could be measured. Now, the equation is basically G times M, right? Well, one parameter, one constant, and one variable. Now I go to the moon, visit the doctor there with the same scale. What is my weight? Something like 10 kg, right? So what has changed? Not my mass. Well, if you do this calculation non-relativistic, mass has not changed, but the gravitational acceleration. So what is the variable? What is the constant here? Is it g or my mass? Are you sure? Both of us fly to the moon and measure the weight, right? And mass is again a variable, and G is constant on the moon, but it's not constant on the planet. What do you do? So the issue with variable and parameters always, you basically can take it as the variable is your measurement, dependable, and your parameters is due to your experimental setup. If you do your experiment on the moon, you have to take into consideration of your local environment. That would be the gravitational acceleration. If you do it on Jupiter or on this planet, it would be different. Therefore, needs to be adapted to get the right information, right? And the information required is actually not the force. That is just the observable. The information required would be the weight, because then the doctor will always tell me something. Anyhow, good. So here, make clear whatever you have that you know is a parameter, right? What are you not supposed to change, which has to take it as is, and which thing you have control of to change to investigate some correlations within physical observables. Okay, so right, so we can set up terms, we can with symbols combine them to equations. Now here I have an example for give as much information in the variable symbol definition as possible. Just now, we already stumbled across the optional argument real and positive. I define here a symbol A0 that is real and positive, right? Put this into the variable, Python variable A0. Then I define an expression. Expression is the square root of A0 square. Now you know the square root of square is just the value. So what's the square root of x squared? X. Okay? Good. So if the computer algebra system in Python works, it should work here as well. Let's see. Does it do something? So here on top, on this code block, I ask for the square root of the square, and it tells me, oh, your square root of the square is just A0. I do the same thing down here, right? Square root of A1 square. I ask, what is it? It's like, it's A is the square root of A1 square. What should I do? So what's the difference here? In top, I told Python it's real and it's positive, right? And if you put in the numbers first, for example, 2, 2 square root 2, 4 square root, 2 times 2 is 4, square root of 4 is 2. Yeah, it works, right? No option. Now, how about I lose the restriction here? I loosen the restriction. Instead of positive, I go negative. So minus 2 times minus 2 is 4, right? Square root of 4 is what? 2. It's not minus 2 anymore. Do I do a mistake? A little bit funny. So actually, whatever it is, it could be plus minus A0, right? So now Python is telling me, yeah, you probably get the absolute value of the thing you're asking for. And because I can't distinguish anymore, plus or minus after the squared operation. You lose this kind of information. You lose not just convoluted in the mathematical procedure, right? Now, how about you square root, you square 1 plus I1? If that is too difficult, we can try, what is it, 2? Is it, no, 3, 4, 5. 3 plus I5 squared. Take the square root. What is it? It's getting a little bit convoluted with the complex terms and so on. So in the most general case, A0 could be a complex number anywhere on the complex plane. And at that point, there are just too many possibilities to come up with a usable simplification. So Python will just tell you the most straight answer it knows, and that is just the expression at that point. Okay, but often we don't have to consider the most general case, right? So you're becoming engineers or material scientists. There's a common saying. Don't know what if you know this, but do you know what's a BMW? You know, the expensive cars. Do you ever ask why it's so expensive? Because in Munich, the engineers at BMW first design a car with N wheels and then consider the special case N equals 4. If you don't like engineering jokes, right? Okay, good. Right, so whatever you know of your problem on simplification, put them in first. Then Simple will have a much easier time to handle your information and provide you the most suitable answer. Okay. What else? Simple will always try to evaluate expressions as much as it is safe to do. Right? Just now I showed you the example of the square root of a square. However, the most general case will always be assumed if not stated otherwise. Again, we have done this before. There's a little bit of a difference here as well. And the symbols where we go into, what is it? Symbols, restreaming on the screen. The example, in the example, we have defined symbol X and Y. We have defined symbols A and B and X. Look here, right? I did a little mistake. X becomes C. So when I ask for X at the end, I get C. Always be very careful at this stage. It is very easy to do a very cumbersome mistake here. Also know that if you ask to print variables, print alpha, beta, gamma, that are defined here in line 4 as symbols alpha, beta, gamma, printing is different from using the simple backend. Right? In one part, I have gamma written out, and in the other case, simple is smart enough to convert them into the nice Greek letter representation. Now, top here, I have something skipped. That is the SymPy printing backend or printing system that is invoked with SP-init printing. This normally tries to even out the printing routines to make the work with SymPy more pleasant to the eye. Let's see if it works here. No changes. Better. Let's wait a little bit. While we wait, we can read the next box. Note the difference to other objects. Example in NumPy. In NumPy, the variable holds a value. In SymPy, we assign a meaning to a variable which does not require to know or the knowledge of the numerical value. This allows us to write general expressions in equations or terms in the form like alpha plus beta plus gamma equal y. It's an underdefined system of equation because we have 3 variables and 1 equation. So the only thing we can do at this point is say, for example, alpha equals minus beta minus gamma. Okay, so there's another method to define symbols that is just symbol. However, so there's a difference to on top. On the top, we use symbols, small s and s in front. Okay. Here, we use now symbol s. I don't like to work with this one, because often I have many symbols to define, and symbol literally just takes one symbol at a time. Therefore, it's less likely to make mistakes, right? But you need to type much more. So we can do this as well. Mathematical equations we have seen before. Well, let's see, does this work? Not sure now if I defined symbols or not. A little bit slow for some reason now. Okay, still works. There are predefined functions available in SymPy, such as square root. Now be very, very, very careful. We know a square root function from NumPy, right? Here I use SymPy. So SymPy and NumPy are basically two very, very different worlds. Right? It's like very, very different. So we would have in this notebook access to NumPy. And instead of calling a square root function from SymPy, but now we call a square root function from NumPy, but we pass an object that lives in SymPy. That will not work. It's like putting your scooter key into a car. Right? Doesn't work. It shouldn't work. At least not with proper modifications. Or better, maybe the key is a good example, maybe the tires of a car, you don't put them on the scooter, right? It's just not meant to be. Okay. So what else can we look at? We can, again, look into the definitions of particular number systems in SymPy. Similar to NumPy, in SymPy we can define integers. Here, for example, using the sp integer method, where num is a number value. We have here an example. This is actually a very, very nice example, because in SymPy we have access to accurate values. NumPy we already know has rounding errors. And I showed you once an experiment with some operations divided by 3, and that scaled somewhere, and there was a big issue with the numerical inaccuracies in Python. With SymPy, I have arbitrary precision. Right? So here, integers have arbitrary precision. I define an integer, the value is 3. Then I calculate here in line 4, 3 to the power of 1000. That's a very, very large number. Right? But the number is given here. Right? And it has a lot of digits. Look at this amount of, it's not ending, you see that? Here, finally. So how do you know that this number is divisible by 3? We take the sum of each digit, and if that sum is divisible by 3, this number is divisible by 3, and therefore it could be a correct power of a base of 3. So far, so good? You can try the same thing with NumPy. You will not get this amount of accuracy. Okay, and then we can check, hey, is the number an integer with this integer attribute? Yes, we can do this. We can do the same thing for float numbers, so basically real numbers. Look at that. I specify a float, but well, we should have arbitrary precision as well. Let's see. So here, sorry, it is displayed as 20, but then the question, is it internally stored as 20? Yes, it is. So we might get around it. So while we can use arbitrary precision in the operations with float numbers and SymPy, must be a little bit careful that at the point of input, we do not fall into rounding errors. But at the moment we have the number defined, it should have quite high, well, in principle, arbitrary precision, because this is one of the strengths of the SymPy packet. Rounded again. Okay, something I need to look into. What happened there since the last update? Okay, complex number next. Oh, we actually should have a break, right? How about we talk about complex numbers and then we have a break. So complex numbers can be indicated in SymPy with the symbol I. Remember on top there were a few symbols I imported, one of them was I. So from SymPy import I, that carries here the information of the complex unit. And then we just need any number plus the complex I times some units, and we have a complex number. Check. Example still work. Num1 is. Does it work? Wait a little bit. Okay, it doesn't do. A little bit slow, maybe. Okay. So then after the break, we continue with rational numbers and functions and expressions. Any comments, questions so far? All right, okay.